In the second lecture, we will study the forces acting on the aircraft during takeoff procedure. Okay, so since we are looking at the forces on the aircraft, and we can see there first the lift and weight acting vertically on the aircraft running along the runway, and because of the engine is working and it provides thrust to the aircraft, so the thrust is pointing to the along the runway. And we can see there are two types of drags acting on the aircraft. One is the aerodynamic drag. That's because when the aircraft is moving within the air, there is a drag produced. And also we have the rolling friction drag. This is because the undercarriage or the wheels of the aircraft moving along the runway. So that's a rolling friction drag. If we are using Newton's second law, we can have this equation, and the force is parallel with the ground. On the left-hand side of this equation is mass times dv dt. dv dt is actually the acceleration, and t minus d minus f and minus w times sine gamma r. You might wonder what is gamma r. And so we'll look at this slightly later. So the drag, we're now looking at each force one by one. The drag, D is an aerodynamic drag. It is half rho v squared times S times CD. CD is a drag coefficient. S is the area. And V squared is the speed of the aircraft. Rho is the density. And then the rolling friction drag, F, is mu times W minus L. So W is weight, L is lift. In this case, during the ground run, the lift is apparently smaller than the weight, is it? So WL is pointing downward. And mu is coefficient of rolling friction, and we will see mu later. And gamma R is actually the runway slope angle. And showing here, the runway is horizontal, but in reality, some of the airports, their runway is sloped. It has a slope angle. And since the runway is tilted or sloped, the weight will have a contribution towards the force along the fuselage. Okay, and now what we are doing is we just rewrite the equation above and make the acceleration explicit. V dot is actually the dv dt, that's acceleration. And so what we are going to do now is try to simplify or analyze this relation in the bracket. Just now we've derived the acceleration of the aircraft on the runway, and we know there are a few component forces on the right-hand side of the equation. And first, let's look at the aerodynamic drag. So we know the aerodynamic drag can also be separated into the parasitic drag and induced drag, two components. So the parasitic drag, we usually denote it as dP. P is parasitic. And the parasitic drag is when an object, for example, fuselage, wing, tailplane, and undercarriage, is moved through a fluid. In this case, it's air. In the case of an aircraft, it's air. So this is basically the friction between the airframe and the air. So that's a friction, kind of friction. And the second is induced drag. The induced drag is a result of the increasing amount of lift generated during the takeoff ground run. So that's related with lift. So we have the induced drag, di. And we know CDI, induced drag coefficient, is related with lift. So the equation CDI equals CL squared divided pi E AR. Okay, so E is also an efficiency number. It is a correction factor that represents a change in drag with lift of a 3D wing. And aspect ratio is B squared divided by S. And this is a wing aspect ratio. And so when we consider the induced drag, we know the wing has a finite span, so the 3D wing 3D structure need to be considered. That's why we have the aspect ratio and E, the Oswald efficiency. And if we name k equals 1 over E pi AR, so we can simplify the induced drag coefficient as k times CL squared. And the CL based on the area field data with consideration of flap deployment. And you know during the ground run, and the aircraft always has a flap extended to have the high lift configuration. That's why we need to consider the flap deployment. And in this case, we can have more lift generated on the wing. Just now we've derived the induced drag coefficient is related with CL square. And when the aircraft is close to the ground, usually within a 1 wingspan, so there is the so-called ground effect. And during the ground effect, it will obstruct the generation of wingtip vortex. We know the wingtip vortex is a source of drag. So in that case, the induced drag will be reduced. And also the lift drag coefficient, lift drag ratio will increase, which is beneficial. And now if during the ground effect, you're flying an aircraft, the pilot will have a feeling of floating or the cushion effect. So when the aircraft is flying close to the ground, and the lower, nearer the wing is with regard to the ground, the more pronounced the ground effect becomes. And while in the ground effect, the wing requires a lower angle of attack to produce the same amount of lift. And now let's introduce the induced drag ratio, which is CDI in ground effect divided by the CDI out of ground effect. And it's related with the height and span. Okay, so h is the height of the wing above the ground, b is wingspan. And in the graph, we can see how kge changes with height. The height is changed from 0 to 80% of the span, and we can see kge increases and closer to 1 at 80% of the span height. And that means ground effect is significantly reduced. It's CDI in ground effect is closer to CDI and out of ground effect. Now let's understand a little bit more how the wingtip vortexes can be eliminated, because the aircraft is flying closer to the ground. There is a higher pressure under the wing, and so this higher pressure will break up the wingtip vortex. Finally, let's look at the rolling friction drag. It equals mu, that's the friction coefficient, rolling friction coefficient times W minus L. And during the ground run, the lift is far more smaller than the weight. Okay, and when the lift is increased, we know the induced drag associated with the lift generation will increase, but the friction drag will reduce on the other hand. Okay, and we know the friction drag, the magnitude of the friction drag is related with a few parameters such as wheel diameter, the weight of the aircraft, wheel deformation, and also runway surface deformation. Those, for example, 4 reasons will affect the magnitude of the friction, rolling friction drag. Typically, the rolling friction coefficient, some typical values can be found in here. For example, if it's a hard surface like concrete, and the rolling friction coefficient is very small, 0.02. But during the brake, we can see last two rows braking with anti-skid mechanism and gives a very large mu, which is 0.7. And during the braking, if the wheel is fully locked, which only gives a 0.4 rolling friction coefficient. And the graph here on the right-hand side shows the how the friction coefficient mu changes with slip ratio during the brake. What is slip ratio? If the slip ratio is 0, means the wheel can run freely. So usually in that case, if it's on a concrete runway, the mu is 0.02 as shown in the table on the left-hand side. And if we are fully locked the wheel, so the mu becomes 0.4. Apparently, according to this graph, the optimum or maximum mu happens not at slip ratio 1, but somewhere closer to 0.2. That's when the anti-skid mechanism is applied. So by applying the anti-skid mechanism, the wheels RPM will be controlled. So in this way, the maximum friction coefficient can be achieved. That's closer to 0.8 in the graph.